Hello, my presentation today is on the 3.2 centimeter cosmic microwave background. I'll explain what that is and the history of its discovery. My slides don't look as pretty or as artistic as Dr. Kane, so bear with me for a bit. The cosmic microwave background, CMB, or the cosmic microwave background radiation, CMBR, was discovered in 1964 by two radio astronomers. The CMBR is a faint radiation that fills all of space between the stars and galaxies, also known as the background, and is completely dark, which means you can't see with the naked eye. It is essentially an electromagnetic radiation left over from the early universe. An optical or radio telescope is best to use and collect data of the CMBR. This is done by measuring the CMBR at certain wavelengths to come up with the temperature of the universe. But first, let's dive into the beginning of how the CMBR was detected. Before finding the CMBR in 1964, in the 1950s, there were two different theories explaining the origin of the universe. On one side, called the steady state theory, it was believed that the density of all matter in the expanding universe remained unchanged due to a continuous creation of matter. In other words, the universe is basically the same at any time and at any place. The other theory we all have heard of is called the Big Bang theory. The Big Bang was a controversial theory of the origin of the universe at the time, and believers suggested that the universe began with an immense explosion billions of years ago. In this scenario, the early universe existed in an indefinitely dense and hot state before the Big Bang caused its rapid expansion. Now you can see the difference between a steady state and the Big Bang theory on what the universe looks like. The Big Bang is more spaced out and spread out, while the steady state looks exactly that, a state that is steady and uniform. Though Edwin Hubble's observation of receding galaxies in 1929 supported the notion of an expanding universe, no definitive evidence of the Big Bang existed until the detection of the CMBR. Before the discovery of the CMBR, it was predicted in 1948 by Ralph Alpher, Robert Herman, who both worked at the findings of Gamow and supported the Big Bang theory. They predicted that some remnants of the Big Bang would still be around today, but would have been cooled by the expansion of the universe. They were able to estimate the temperature of the CMB to be about 5 K, though they re-estimated it to about 28 K 2 years later. The evidence they were looking for was accidentally found almost 20 years later in 1964 by Bell Lab scientists and radio astronomers Arno Penzias and Robert A. Wilson. In 1959, Bell Labs built a 20-foot horn-shaped antenna, nicknamed the Horn, in New Jersey that was to be used with an early satellite system called Echo. The horn was used to bounce radio waves off metallic balloon satellites in order to transmit signals from one part of the world to the other. But after a few years, another satellite was launched and Echo became obsolete. When the horn antenna was no longer used for commercial applications, it was free for research. In 1964, Arno Penzias and Robert A. Wilson, shown in the picture with the horn in the background, jumped at a chance to use the horn antenna to analyze radio signals from the space between galaxies. When they began to use the antenna, they heard a persistent noise of microwaves that came from every direction. This noise interfered with their research, so they had to find a way to remove the static in order to continue with their experiments. They did everything they could to remove the static noise. They cleaned the horn thoroughly, even removing pigeons that were nesting in the antenna. After exhausting every possible explanation for the sound's origin, they realized they had stumbled upon something interesting. What they actually discovered was the cosmic microwave background radiation, which later in 1978, they were awarded the Nobel Prize in Physics. Can you imagine that? Getting the Nobel Prize for accidentally discovering something. So what does this mean? The findings at the horn was actual evidence that supported the Big Bang theory. The CMBR is believed to have formed around 380,000 years after the Big Bang and contains clues of how the first stars and galaxies formed. This was an important source of information on the early universe because it is the oldest electromagnetic radiation in the universe. After much calculation over the years, it helped give rise to an estimated age of the universe to be 13.8 billion years. The CMBR also showed the temperature of the universe to be around 2.73 Kelvin. This indicated that the early universe was incredibly hot, just as predicted by the Big Bang Theory. Since the Big Bang actually requires that there be a cosmic microwave background radiation, the discovery of the CMBR was one of the several strong reasons that drove the Big Bang Theory to be accepted amongst the scientific community. Now let's discuss what the 3.2 centimeter CMBR means. Since the CMBR is a faint radiation that is completely dark, a radio or optical telescope is used. An optical telescope gathers and focuses light from parts of the electromagnetic spectrum to create images. A very sensitive radio telescope, such as the horn antenna, shows a faint background noise or glow that is not associated with any star or galaxy. This glow is the strongest in the microwave region of the radio spectrum. Now, light comes in a range of wavelengths from the shortest wavelength, gamma rays, to the longest wavelength, radio waves. Microwaves are the name given to radiation between infrared and radio region, with wavelengths typically being in the 1 millimeter to 10 centimeter range. The CMBR is best detected at a 3.2 centimeter wavelength, and it reveals the temperature of today's universe to be 2.73 kelvins. At the horn antenna, the wavelength was measured at 7.35 centimeters with a temperature of 3.5 Kelvin plus or minus 1 degree Kelvin. The main reason for using short wavelengths is to reduce the collection of atmospheric radiation, which corrupts data collected. Atmospheric radiation increases rapidly for wavelengths less than 2 centimeters. An in-depth explanation of a 3.2 centimeter wavelength measurement is very technical because it involves different forms of radiation and black bodies, which we haven't learned yet, and I don't have the time to discuss in greater detail. A lot of people ask as if you can see the microwave radiation, and you actually can when you look at a TV set. When you look at a TV set and you notice the snow in the background, a few percent of the snow on the TV screen is actually noise that is caused by the background of microwaves. Now here's a picture of the background radiation. The temperature of the CMB is almost completely uniform at 2.7 Kelvin. There are tiny variations in the temperature, as you can see from the different colors in the picture. The dark blue indicates colder regions and the red indicates warmer regions. These colors represent high density fluctuations in the early universe. With the help from gravity, after billions of years, these fluctuations evolve into planets, stars, and galaxies. As you can see over the years, the images have gotten much better. And today's image of the microwave background is this. So in conclusion, there is much that hasn't been discussed regarding the cosmic microwave background. It's interesting that the CMB was accidentally found in 1964 by Bell Lab scientists Arnaud Pinzayas and Robert A. Wilson, who later received the Nobel Prize for their discovery. This discovery impacted the scientific community with evidence that supports the Big Bang Theory and the origin of the universe, by showing that the early universe was extremely hot and dense. It also helped estimate the age of the universe, which is to be 13.8 billion years. This discovery also led to the understanding of the universe's temperature. By using radio and optical telescopes looking at 3.2 centimeter wavelengths, it is estimated that the temperature to be around 2.7 Kelvin. Today's technology has been able to put this information together to create a picture of the universe and to help create better models of the origin of the universe. Thank you for your time.